And finally, we make it to the 20th century. Yay, we made it. 1903, Mikhail Tvest invents chromatography, an
Dang.
important analytical technique. Yep. 1905, our,
I mean, that's not that big of a deal.
our heroes, Fritz Haber and Karl Bosch. Yeah, just like, feed all the planet, that's it. Fritz Haber and Karl Bosch developed the Haber process for making ammonia from its element, which was a milestone in industrial chemistry with deep consequences in agriculture, as we have already highlighted in our second law of thermodynamics clip. In 1907, Leo Baekeland invents bakelite, one of the first commercially successful plastics. Sorensen invents the pH concept and develops methods for measuring acidity. 1912, William Henry Bragg and William Lawrence Bragg proposes Bragg's law and established the field of X-ray crystallography, an important tool, for deducing the crystal structure of substances. 1912, Peter Debye develops the concept of molecular dipole to describe the asymmetric charge distribution in some molecules. By the way, this area we are going to be exposed to a lot when we go to statistical mechanics to understand why it's critical there. In 1913, Henry Moseley abolishes pretty much Mendeleev's periodic table, and working from Van der Broek's early idea, introduces the concept of atomic number to fix the inaccuracies of Mendeleev's periodic table, which he had based on atomic weight. 1913, Frederick Soddy proposes the concept of isotopes, that elements with the same chemical properties may have different atomic weights. In 1916, that guy is very critical to so much stuff in chemistry. He publishes the atom and molecule, the foundation of valence bond theory, and in 1923, along with Merrill Randall, published Thermodynamics and Free Energy of Chemical Substances, the first modern treatise on chemical thermodynamics. And that's where the electron pair theory of acid-base reactions has been developed. If just like, if it somehow sounds like Lewis acid or something, sounds familiar, that's the dude. 20th century. This area is going to be like awesome. 1927, Fritz London and Walter Heitler apply quantum mechanics to explain the covalent bonding in hydrogen molecule, which marked the birth of quantum chemistry. 1931, Eric Huckel proposed Huckel's rule, which explains when a planar ring molecule will have aromatic properties. Just think about like that for a second. Like, he has a rule that basically tells you if a molecule that basically the structure of it has a planar structure, when it will start having aromatic properties. 1931, Harold Urey discovers deuterium by fractionally distilling liquid hydrogen.
Wait!
1931.
Distilling liquid hydrogen?
Just think about that. That's why I was like, I wanted to be like, going into the detail. Hydrogen that almost exclusively, if you look at the phase diagram for hydrogen, exists only in gas. Was like a PS dot at the bottom, like far left, like bottom left bottom there. It's like, if you reach there, you can have liquid and solid. Like by the time you reach the liquid form, it wouldn't take much to be getting solid. But the part like really outstanding about like Harold, the fact that he was able to get there and separate two different types of hydrogen.
That's
like
absolutely
deuterium
insane.
and hydrogen.
I mean, that makes
by
no sense.
distillation. In 1931. I'm just gonna keep stressing 1931. I'm sorry. Anyway.
It was 100 years ago.
It makes you proud.
That's insane.
It makes you so proud, and it's very disappointing at the same time. In 1935. 1935. Wallace Crothers. Sounds familiar, Brandon? Leads a team of chemists at DuPont who invent nylon, one of the most commercially successful synthetic polymers in history. So keep in mind, polymers as we know it just came to be made in 1862. Nylon came later on in 1935. So polymers as science, it has been there in 1862. Just think about it. 2 centuries. 1939, Linus Pauling published The Nature of Chemical Bond, a compilation of decades worth of work on chemical bonding. It's one of the most important chemical texts. It explains hybridization, covalent bonding, ionic bonding, and as explained through electronegativity and resonance. And among other things, the structure of benzene. So that's basically what Linus Pauling did. It's a huge deal. He also used X-ray to deduce the secondary structure of proteins. I mean, it's pretty like we are far early to be talking about this, but protein has several structures: primary, secondary, and tertiary. In terms of complexity, we're gonna highlight that very later on. But pretty much he was able to be actually using the X-ray to, to differentiate a primary kind of protein, like a primitive one, from a more complex structure secondary protein. That's 1939. 1944, Robert Burns Woodward and William von Eggers-Düring successfully synthesized the quinine. That's the same chemical that previously the guy by accident invented the dye because he was trying to make quinine from coal tar. He couldn't, so he invented the dye. And instead, those guys came later on to make quinine successfully. This achievement, characterized by fully artificial chemicals as a source for synthesis process, opened an era called the Woodwardian or chemical era, when many drugs and chemicals as well as organic synthesis methods invented. Due to the growth of chemical industry, many fields has grown, such as the drug industry. So 1944, Woodward and Düring, those were the critical milestone for the drug and pharmaceutical industries to start. That's the launching origin there. Alan Walsh pioneers the field of atomic absorption spectroscopy, an important quantitative method that allows one to measure a specific concentration of a material in a mixture. 1953, our geniuses, those guys were geniuses, especially the first one. James Watson and Francis Crick proposed the structure of DNA, opening the door to the field of molecular biology. That's why that picture up there is dedicated to them. It's literally that's the decade of Watson and Crick. 1957. This guy also is a critical dude. I mean, once we go into biochemistry, you're gonna know how critical that is. Jens Kuhn discovers the sodium-potassium adipase, the first ion transporting enzyme, and pretty much that's the critical part, describing the sodium-potassium pump that basically provides energy to every part of our body. Whether we are moving or not moving, the sodium-potassium pump is basically what generates energy for us, because it's moving electrons all over the place. Anyway, we're still, I guess, in 20th century. 1962, Neil Bartlett synthesized xenon hexafluoroplatinate. This is the first time for someone to show that noble gases can form chemical compounds, and they are not 100% inert. If you give them the motivations, they will move. 1965, Robert Burns Woodward and Roald Hoffman proposes the Woodward-Hoffman rules, which uses a symmetry of molecular orbitals to explain the stereochemistry of chemical reactions. 1966, Nozaki and Niori discovered the first example of a symmetric catalysis. It was mostly around hydrogenation, by the way, using structurally well-defined chiral transition metal complex. 1970, John Pople develops the Gaussian program, greatly easing computational chemistry calculation. 1971, Chauvin offered an explanation of reaction mechanism of olefin metathesis reactions. 1975, this guy is going to be a long thing. Carl Barry Sharpless discovered a stereoselective oxidation reactions, including Sharpless epoxidation, Sharpless asymmetric dehydroxylation, and sharpless oxyamination. I'm telling you, this guy you know,
That's
put his
really
hand is a
cool.
very critical knob there. Yeah. 1985, Harold Croteau, Robert Curl, and Richard Smalley discovered allotrope of carbon
Oh
called
yeah.
fluorines. You remember
Yeah.
the carbon
Yeah.
nanotubes? Yep, that's the one. A class of large carbon molecules superficially resembling
Right.
geodesic dome. Then followed by that, in 1991, Somio Lejima uses electron microscopy to discover a type of cylindrical allotrope of carbon
That's really
known as
crazy,
carbon
though.
nanotube.
Yeah.
Thro-
Man, that wasn't
Yeah.
that long ago.
So
that was like
that's
30
pretty much
years.
it was a
That's
continuation.
insane.
Yeah, absolutely. And last but not least, in 1994, Robert Holton, first total synthesis of Taxol. And that's pretty much like the history of the chemistry, like as you know, in a nutshell, as a snapshot. Now, moving to the calorimetry and chemical reactions, and the reason why we needed to address that is because till now, beyond highlighting how critical the history of chemistry is, before going to the chemical engineering or chemical thermodynamics itself, the part that we needed to understand is that we are going to address chemical reactions. So the first thing in chemical reaction, how we actually, you know, how can we calculate or how can we measure experimentally the heat is being liberated in a given reaction. So for a start, the first law of thermodynamics, as we see on top here, you have the dq, like the first law is like dq cvdd plus bdv. The pdv
Right.
is the work, the dq is the heat,
Right.
cvdd is the internal energy. So if I take that equation with respect to, you know, take the derivative of temperature at constant pressure, it will give me rate of change of heat with respect to T at constant pressure, the same for CV, for the same on the side P dVT. So from this side, what's that? This is what we know now as the specific heat at constant pressure. That's basically how the fundamental equation came from. Now, this is gonna be 1 because it's the, you know, it's the derivative of temperature with respect to temperatures. This is gonna be 1. And we conclude this relationship, which is basically says fundamentally the heat capacity at constant pressure is related to heat capacity at constant volume plus P dV dt. So if you have the equation of state, irrespective of what equation of state or activity model, we didn't speak about activity models yet, but irrespective of any equation of state we use, you are going to find out that the specific heat at constant pressure will always be bigger than a specific heat at constant volume. This is a thermodynamic fundamental fact. So if you ever come across where you find the sensible like CV is more than CP, you better be checking out your equation of state again, because your equation of state is going to be wrong if
And
it
that
comes up with
expression on the
something
right
like
is
that.
a constant, right? What is the name for it? The PdV.
The CV or the no, that's not a constant. No, that's not a constant. This is a thermodynamic relationship. So from the whatever equation of state you are going to use, you are going to, like to say, PV equal RT. In that case, CB is equal CV plus R.
Yeah, you got
Like
me.
if you would
That's what I'm
use the
thinking of.
ideal
Oh,
gas,
I'm sorry. Yeah, you're right. Yeah.
that if you use the ideal gas, that relation would be
Yeah,
CP
right.
equals CV plus R. But like in real life, it's not R. It's more than that.
Oh,
It's going to
no
be like
kidding.
different than R.
Okay.
So just like you know, yes, that's why I had to
gotcha,
write
man.
it
I
this
was
way
gonna
as a
ask.
fundamental
Okay.
thermodynamic equation. Because why this is so why I mean
Right.
it's a different topic. Why this is super critical? Because we're gonna address this later on. But like whenever someone is coming
Right.
up with an equation of state and basically say, hey, I found out an equation of state XYZ, the first validation is that you have to put it to the test in this fundamental relationship. If it end up making the CP less the CV,
Nope.
that equation
Oh,
of state is
okay.
invalid. just right
Yeah.
away. Yep, that's how, because like you can never find any material in life that the specific volume as it
Right.
changes with temperature is going to be ever negative, right? So, and of course, like we're talking here about like sensible heat, you know, so people wouldn't be like talking about like ice on water because that's a phase change, that's lambda. So just so anyway, the graph that we have now, that's the calorimeter, and basically like you see there, it's a constant volume. And what happens is like you get the material that you're testing and you ignite it, and you always make sure that the water surrounding it is perfectly mixed, you know, to make sure that there's no heat transfer profiles or something like that. So you ignite your reaction and you make sure you're a constant volume. It's the bomb itself that you see in the middle there is constant volume, and you basically measure the temperature, how the temperature changed, and that's how like the enthalpy of formation at basically at standard conditions are basically found or experimented. How you experimentally find something like that. And then the reason why you have this picture along with this relationship is that in reality, what you can actually measure is CV,
Right.
you know, for the water. You already know the CV of water. But if you are dealing with a continuous open system, you are going to need to deal with CP. And that's why the CP had to be like coming up in our slide right now to make sure, like, you know, if you are doing something at constant volume, it's really easy to transform it into constant pressure through that way. So, first law of thermodynamics and the heat of combustion, and that's how like you can come up with something like this. If you have an oxidation of methane, pretty much the standard enthalpy of combustion, what does it mean? It means that I have done this kind of combustion in this type of calorimetry at standard conditions. And that's why that enthalpy of reaction has to be specific at a given
Right.
reference of T and P, which is in this case 25 Celsius and 1 bar. Which again, in our next episode, we're going to be clarifying why this is super critical. And it's going to be related to the fact that enthalpy is a state function and it's going to be a huge deal for us. Now, so to summarize what we have, how chemistry evolved across human history, how the global demand for the chemical revolution paved the way for thermodynamics to go beyond heat engines, how calorimetry and heat of reactions are deducted, how specific heat at constant pressure relates to specific heat at constant volume. And with that being said, I don't know who's that guy in the bottom left, but yeah, so I would say up next we're going to talk about like how adiabatic flame temperature is calculated, how matrix application in deducing a set of independent chemical reactions. We are exclusively using the mathematics to just like get a clear cut of like how we apply this in chemical reactions or chemical engineering without extra.
And for
extra
those
details,
unaware,
pretty
like
much.
those,
How the matrix.
what you see there, the matrix application, that's where you're really going to start getting to the meat of how do you actually put this stuff into practice. So keep posted for that.
Absolutely. And we are going to be going beyond just like applying this for a set of chemical reactions. We are going to go to, I know lots of people have been waiting for this moment. We're going to be highlighting the matrix application to steam methane reforming reactions. And we finally close that statement regarding, how steam methane reforming chemical reactions looks like from thermodynamics perspective. And last but not least, we are going to be like having the industrial approach to steam methane reforming chemical equilibrium. I hope this episode has been very informative. Please feel free to be like reaching out to me or Brandon by email or on YouTube. And we are going to be doing our best to get your questions or any recommendations that you might.
Yeah, I'll speak
propose
for
us.
myself.
Thank
I
you.
really do want to get some questions out there. I know that for those unaware, Muhammad and I's relationship actually started off with me asking him questions, right? And I would not be the engineer that I am today if not for him answering those for me. So I really want to say thank you for watching or listening, however you enjoyed. We really do appreciate it. Hopefully you learned something. If you did, go ahead and let us know. So you can send us an email to you can send an email to sciencemadesimple@outlook.com. There's a link in the show notes below. Watching on YouTube, go ahead and like and subscribe. If you got a podcast, go ahead and subscribe, leave a comment, leave a review, let us know what you think. That's all I got. Signing off.